Alright, welcome back to another video of the part 2 to the new series that we are starting, where we do an outbreak and then we cover the global tropics. This time we're going to have no waffling. Like last time I was speaking around too much and edit some parts of the video out. This time we're going to go straight into the case study and then straight into the global tropics. So without further ado, let's go. Alright, on June 16th, 1992, we had a very significant outbreak. This produced an F5 tornado in Minnesota, the most recent F5 tornado in Minnesota, and the outbreak itself had caused 64 injuries and 1 fatality only, despite there being numerous significant tornadoes over multiple states, including Minnesota, South Dakota, and Iowa, and Nebraska. There are 65 tornadoes, making this one of the significant high-end OIs outbreaks, as Tom Gruzoulis likes to say, for June standards, and so it's one of the largest June outbreaks and most significant outbreaks on record in June. And June is also considered part of the tornado season, the spring to summer tornadoes. So the F5 tornado, the main story really of this is what we're going to be discussing, and this tornado was one of the strongest ones in Minnesota history. Path length of 16 miles, path width of 280 yards, and it had caused the 1 fatality. As a whole, it was an outbreak sequence. An outbreak sequence does occur quite often in June. However, the outbreak sequences are quite small and tend to be limited in the amount of tornadoes that are produced. And typically they do occur in northern plains, so this would follow climatology much more favourably than as an unusual anomalous outbreak. In this sequence, the 3 days from June 14th to June 16th, and there was 1 F5 tornado, 3 F4 tornadoes, 15 F3s, and 33 F2s. There were 170 total tornadoes in this, and 2 of the other F4s occurred on the other day. 1 F4 occurred in Kansas, southwest of Beloit, on June 15th, and the other one in McPherson, Kansas as well. Now looking at the SCUT and hodograph, this is the parameter soundings for the F5 tornado near Chandler, Wabasso, Minnesota. This is a recreation sounding that is used based on some of the observations and generating a sounding that is based on what the models kind of predict that the environment synoptics and mesoscale were like at the event, so giving us a modern sort of idea of what the outbreak could have looked like. And so on the left is the SCUT. This is where we're going to look at one of the main parameters, which is the instability. And so we normally talk about 4 parameters. We talk about the instability of the lift and the wind shear, as well as the moisture. And so the moisture and instability is what's specifically highlighted in this sounding on the left to the SCUT. And so we got the temperature and the dew point trace going up into the atmosphere, and then we have the air parcel as it lifts across the atmosphere, and the area in between the temperature spread and the air parcel is going to be the region of which will be used to measure the instability. And we typically like to use mixed layer CAPE rather than surface-based CAPE, because surface-based CAPE assumes a very thin layer of buoyant air that is being ingested by the storm close to the surface, and so it does not account for the instability aloft where the supercell is particularly growing in the mid-levels and the upper levels of the atmosphere. Now this might not be the most typical sounding for SCUT. In fact, there is a temperature inversion near the surface. So again, this may be just the depiction of what the surrounding was like, but we have a little bit of an inversion. This would have somewhat implied that the base of the storm would have been elevated, as this warm nose is quite sharp on a gradient just above 850 millibars, but the observations from the real time suggest not. So that may play in as a potential bugaboo, but one bugaboo that had changed throughout the outbreak and through a mesoscale interactions which would have potentially reduced the influence of such a warm nose, because typically you would associate with this with high bases. We also have not as much instability in this region, only around 1000 joules per kilogram of mixed layer cape, that is around the margins for these strong supercells, large supercells to be developed. One other thing to also note is that the warm nose would mean that the wet bulb zero, so you would look around 850 millibars, that would be the wet bulb zero is elevated above the warm nose, and to erode this sort of inversion you would most likely need to have some sort of merger-nudger interaction to avoid such high bases, and so that would allow such much more of a lower mesocyclonic rotating wall cloud that would provide for such a large tornado to even develop. Sometimes in the event of even being some sin, so you have minus 100 sin, and this is during the observations of the event, this can be negated by much stronger shear and for these rotating supercells to develop. And if they already are mature by development and then the inhibition kicks in during its development stage, then that negates the effect of the sin, thus providing the supercells with quite a sculpted structure, as well as having not as high of a initial wall base from the surface. The lapse rates are not very significantly high, however they are at least around the minimum mark of just above 6.8 to around 7 degrees Celsius per kilometer, and so that is on the margins for the favourable supercells to develop in. One of the things is we have 67 over 71, and we have quite a dry profile aloft from the instability, so that would produce less of a wet instability profile, and there's less humidity, thus providing these much larger supercells that are less likely to become outflow dominant. Looking at the holograph, we have a very strong shear, which is also in part, as mentioned before, very favourable to avoid such effects of a warm nose, but also just for rotating a storm, the potential for rotation is very significant around the 0 to 3 kilometer SRH, which would be the area measured in the yellow shaded region, which is around 400 meters squared per second squared, much more above average and much more in the class of where violent tornadoes can occur. And shear again is the number one parameter really in trying to decipher the significance of violent tornado potential. And so when you have such favourable low level shear alongside deep layer shear of 50 knots, you have fairly large storm relative inflow. You are going to have much more of a larger supercell with strong low level rotation evident. Looking at the streamwise profile, we have 90 to 80% within the first 3 kilometers. Typically above 2 kilometers it dips off quite quickly, but we still have 80% streamwise vorticity within this 0 to 3 kilometers, particularly within the lowest 0.5 to 1 kilometer, which is as expected. But in terms of the amount of streamwise vorticity being streamed into that, we have very high numbers in the 0.5 kilometers, and that is almost double what is required for these very significant storms to produce these violent tornadoes, and just for even favorable tornadogenesis to occur. And so we have much more above the threshold. So this storm likely ingested so much storm relative streamwise vorticity, and so much of that vorticity that there was enough vorticity stretching with the low level shear overlapped to produce efficient tornadogenesis. And so whilst the tornadogenesis would have been efficient, it would have also maintained vorticity stretching along a much larger region. So you would not have wispy condensations streaming down from the base, and you would have likely had one much larger area of condensation along whatever part of the mesocyclonic wall cloud that forms. And that is what we're going to display in just a second. This is the image of the Chandler F5 tornado, and in this you can see much more evidently what I mean, as in the bases are much more lower. You can see sort of to the right of the, and so if you look onto the right here, you will see all this sort of storm relative streamwise vorticity that's streaming into the tornado, and you have this very large mesocyclonic wall cloud. You would have had a lot of vorticity stretching rather than having these wispy condensations that develop along the low pressure system that is going to produce the tornado along the wall cloud. Instead of these wispy ones that you see sometimes that become multi-vortex, you're going to have a much larger area of condensation that rapidly develop, and that is due to this. If you have such a high value and such strong low level shear, you will see almost screaming inflow, probably very strong inflow from this. I would imagine probably upwards of greater than 80 miles per hour at least, and you would have had an RFD as well, very efficiently wrapping around the circulation. As that tightens and narrows the inflow, the tornado can expand very rapidly in that sense. And the tornado itself has very violent kind of characteristics. You've got this sort of left edge lean. This, what we typically associate on this is like a left edge lean. This is typically what you see in these violent tornadoes, and you often you see this deep sort of condensation near the surface. Some tornadoes that are large and wedge shaped can have this sort of wispy lack of condensation around the corners, and that kind of tells the idea that this is just more of an outer circulation, and there's no real core evident. Like when you see these tornadoes, you can almost immediately tell just by look. It's kind of hard to describe because there's not much in research directly explaining this, but typically for even like Beauregard in 2019, you would have this sort of feature here, and typically the core would be evident in here, assuming it's a single-celled model for tornado. And this is some damage taking near Leota. So we've got a lot of significant damage. Nowadays, I would say some of this damage would probably be more reminiscent of EF4. This sort of damage you'd see nowadays probably would be rated EF4 around anywhere between 170 to 190, depending on how large the structure was, really. But again, it's still a very significant damage, violent intensity damage, but that is just something to notice. More impressive damage feats are such as mangling the vehicle and mangling the frame, and having this sort of partial debarking of the tree limbs. And we do even have a video of the tornado itself. I mean, you can just tell from the video alone just how aggressive the rotation is. You can really see it in this. Like, just look at the rotation here along the mesocyclone, and you can see such strong RFD. Like I said, like you've got such strong RFD around the circulation, and then you've got the ground circulation here. The last thing I would like to share is if you search up the Lake Wilson F4 tornado, which also did occur, and you can see just right here, there is practically no imagery of this F4 tornado as far as I'm aware, a lot of random sporadic pathways you can see of the tornadoes as well. Like this most likely is an occlusion or a deviant motion right here. But you've also got the F5 tornado, and you've got this F4 tornado that's going the other path, probably part of the same supercell. You've got multiple tornadoes going at the same time. So a very strange setup, but again, two violent tornadoes impacting the same region, and on just by search you cannot find the F4 tornado. So if there was any lost media, that would be great to see just the lost media of this F4 tornado. And also, it is quite a rare scenario to see an F1, F5 impact the same region, Lake World. Alright everybody, on the second part on the global tropics, I had previously done an update, but that was outdated, so now we're continuing with this new, more updated information. So looking at the tropics, we're going to ignore 98W and 99W. They're not as much of a concern as of yet. More guidance hasn't really been depicting as much development lately, so we're going to be kind of looking away from them just for now. In case they do develop more, then we will go back to them and discuss them. But currently we have Tropical Storm Barry and we have Tropical Storm Flossie, and Tropical Storm Barry is of some question that was put earlier about how its development will be. Would it actually be classified as Barry? And now it has been named, and we're going to discuss that system. So first, if we just look at the Atlantic NHC outlooks, currently we have Flossie. By their analysis is 40 miles per hour, 1005 millibars, and we do have a 20% invest. This does make sense with the model guidance hinting, especially the GFS, but the GFS obviously can be outlandish when it's outlooks, not so much for the Eastern Pacific, but still it can be a bit aggressive. But we have more of a total agreement between all the models, and so we have this increased probability now of 20% of something developing and moving up west, which is actually different to most of the storm tracks so far, which have been west-northwest to northwest and then due north potentially before they dissipate. And this one's more west, where it should track and probably be quite a high ace maker should the system develop and push out westwards. In the Atlantic, the NHC just made a new update, increasing Barry to 45 miles per hour and 1006 millibars. It's quite interesting. I think we'll see if that stands, because it was looking like the intensity was actually lower than it actually appears. So, but we do have an upgrade to that, and we also have this 20% invest, which is quite interesting as well, because some guidance has actually been pushing this this area of probability with a system that pushes west rather than east, which is the energy is hinting at an eastward movement, and more alignment is coming closer and closer, and more guidance is pushing out east, but there are still some westward tracks. And I think the GFS did hint on the westward track and the Euro, but the Euro has changed now towards moving on an eastward track. We're going to look at this loop, and you can kind of tell that there is something going on here. So you can kind of ignore the static here. You might see some static right here, but you can ignore that for now. But this is just the precipitation. So it's like almost like a curved there's a curved rain band, which is like a shield that out ahead of the actual circulation. The circulation more so is around here, and you've got some semblance of the most intense winds around a closed circulation around here, and so it's been recognized as a tropical storm. It by radar it does look more convincing than visually, but generally for the most part the system has not really been looking as tropical. I guess now it does stand valid that it is a tropical system. It's not the neatest looking, and it could have not even been considered tropical for the most part, but now with a bit more of radar, and we also have a increase in the development of the system on infrared, which we'll look at right now. So you can just see how the system has been developing over time. It does look very, very messy, and Barry, the name, does have a history of quite the not so good looking storms in terms of photogenic from satellite appearance, and also just from an understanding of what this tropical system identifies, more so as it kind of, this one more so is leaning on less of the tropical storm side as it looks visually, And on radar there is some more convincing evidence now that we can call it a tropical system. Before, it's more of a PTC, a potential tropical cyclone, developed low. So it became like a tropical. So basically, the timeline is it became a tropical depression, and then it got reduced to this PTC type of low, and then got increased now to what can be understandably a tropical storm. The system did have quite an open circulation, and so holds on to that sort of idea. Not as evidently, but the main center is down here. You've got this heavy precipitation out up front and out here, and they're not really focused around the circulation really. You've got some convection that's around here. It's not really rotating around, but it is pushing across and is part of the system's overall area of influence circulation, and so you do see it follow the system more so as a heavy precipitation, and you can just kind of see they kind of just flare up. This is very monsoon looking, so it does not look like a tropical storm really at all. But the system, again, by radar, kind of reflects more so tropical storm characteristics now than earlier. So by marginal extent, it is now. So the estimates for Barry have, for Dvorak estimates are pushing towards 50 miles per hour in this, with NCCF and SIMS DVTO, and we do have deeper and AIDT, which is also around 45 miles per hour. So interestingly enough, it does actually seem like 45 miles per hour is the right call here, and they are. This update is about 40 minutes off, like, so that's quite a recent update then from these observations, and so I tend to believe so that the system might actually be of what the NHC has identified as 1006 millibars and 45 miles per hour. I think that's a good call for the intensity of the system currently, and so I do think this is the analysis that we will be calling for as well. Again, if you are interested in the updates, there are multiple updates on the channel currently up on my X account, which has these updates on the global tropics. We had one earlier for the 06E in the Eastern Pacific, which now is Flossie, and now for O2L, which is Barry. And so you can check the new updates that will be coming out as the video is uploaded. With this, we're going to move on. So for Tropical Storm Flossie, so just playing the loop for Flossie and seeing how the evolution plays out. You've got the system which has had a very good development. It's maintained its convection, and it's had this healthy sort of inner circulation where the strongest winds are, with still largely a broad circulation, a very large area of influence, in particular when you talk about cloud to cloud. But the system is looking much more healthier. It might have somewhat of a waning effect because of Barry on the west, on the other side, and so that would probably cause Barry's inflow channel and its area of influence to partly disrupt the circulation of Flossie. But on a large scale, the distance still is enough where it will not be all too significant. Barry might be stalling just because of the influence of Flossie, so there is still that sort of indirect interactions that are taking place. But with Flossie in particular, again, the system has some waning convection, which is still typical, especially in the early stages of development. It kind of looks quite messy, but this looks like a very healthy looking tropical storm, much more in comparison to Barry. And you can see, for the most part, this part is a remnant of the precipitation of the previous curve banding. You've got some more further development out here. You've got the center of circulation here. Some of the lesser convection is, but you've got this healthy sort of shape that is like, it's almost like a C shape right here, because you can see the C shape like this, but you've got this healthy structure where you've got this inflow channel, you've got some decent outflow across, you've got some, there's likely some shear imparted here because you've got this sort of waning convection, especially to the north side and all around, and then you've got some heavy precipitation on the backside. This is just from that strong convergence and an upper level divergence that's causing a lot of lifting with convection over the Pacific. And you've got this region here where the circulation is. This will be your CDO. and the system is already in a vertical alignment phase. This will mean that the system should eventually have the mid-level circulation, low-level circulation, low-level and the mid-level aligned together. If we play the loop, it should kind of show how this plays out. So the circulation almost is. So the circulation has the mid-levels around here, and you've got the low level as well. So you've got almost an alignment. So the system's already ready for intensification. The Dmax happened earlier, so you got some increased convection, and you've got this warm pool of sea surface temperatures around 31 to 30 degrees Celsius along the eastern coast of the Eastern Pacific, and you've got an extended OHC values around this region as well, which is going to be favourable for potentially rapid intensification, which will be greater than 35 miles per hour within a 24-hour period. And so you've got this true healthy tropical storm that is likely to develop and intensify. And one thing I have to put a precaution on is these intensities can be greater than what they are modelled by. So the guidance, typically when you look at all the squiggly line models, they tend to underdo it. This is our current squiggly line model, and you can see that they've now increased to the category 1 within 48 hours, and the NHC is kind of in line with this squiggly line graph. But again, the one main consensus is, whilst you do have this average of this development, looking at the actual environment, ambient conditions, not just the models themselves, the favourability of this could be far more than what the models could be depicting. That's the upper boundary, an upper echelon that we've already seen with Eric. Eric's main consensus started reaching category 2 as it started to explosively intensify, and it actually reached category 4 status. So we had almost a 2 category gap from the models, and that guidance was very late to finally hint on its intensification. And so from early on, these robust models probably are more representative towards the potential maximum bounds and where the system could be because of the environmental favourable conditions. You've got this extremely favourable environmental conditions rather than a medium favourability, which is likely calling for rapid intensification, but more so alongside these modelled squiggly lines. But again, the upper echelon boundary is something to always consider, especially after you've just seeing Eric giving a perfect example of that already early in the season. One great tool actually that's now just become available here is the rapid intensification probabilities, and we can actually see quite a high probability right here. This is actually a very high probability within this sort of phase. You've got these two ones here, and you've got this one here as well. You've actually got quite a large range of rapid intensification, and you've got some extremely rapid intensification values approaching almost here. So you've got a pretty good stretch of intensification numbers that could occur within this favourable ambient conditions, which the models are not depicting at. So this is also another really good guidance to already suggest that the system could develop more than it is hinted. The intensification process is probably already underway, and one of the things is once the system finally has vertical alignment, there will be very little in any sort of ways to induce weakness on the system until it finally reaches near Baja, where the temperatures cool off rapidly, and that's largely in part due to the current negative DPO phase with all this cooler sea surface temperatures, and that are pushing from the equatorial Pacific, creating a cool region. Also the North Pacific high being dominant, and you've got these strong winds that are cooling off the sea surface temperatures from the Ekman's current, and you've also got this oscillation phase that will keep those temperatures at bay until peak heating during September, August will increase those values. Tropical Storm Flossie, the SIMS into CF DVTO is calling for 40 miles per hour and 45 miles per hour, so an average consensus around that. And we do have DPRIN, and we do have AI DT as well. It's calling around 40 miles per hour as well. So I do think 40 miles per hour is a pretty good call here as well. Looking at the satellite appearance, we can sort of agree with this. If we just look at this graphic here, this can kind of give us a manual euphoric observation, and the manual Dvorak observations, what you really want to look at is this T3 phase right now, where you've got this large spiral shaped system. You don't have this sort of stage yet where you've got this shrimp feature, but you've got this curved, weak circulation, large banding, you've got some banding to the south, and you've got this precipitation shield with a developing circulation which is reaching vertical alignment. And so when you have this sort of C shape as I described, this T3 is tropical storm phase, is a phase, and it's in between this 3 and this 4, because intensification will mean that it will increase by each point value. To show you what I mean is, if you look at this figure here, you can see that we're looking at the system around 2.5 approaching T3 right here, and this is where the system is in between currently, but it will also be pushing towards 4. So the system right now is in between this, it's pushing 3 as described, and the system is approaching 3.5 with a rapid intensification after it has settled on this T3 number. And so with manual Dvorak also agreeing, I tend to agree with the system having an intensity around 40 miles per hour and roughly 1006 millibars, not too different to Barry's intensity currently, but is expected to be much greater in the future. Alright, with this, we don't have any new microwave observations on the system. You've got this partial observation, but with this I'm going to end it here. If there's any questions, then do comment below, or do go to the X and ask, or just support and let me know about this video. So without further ado, I will see you guys in the next update.